For the K problem, there are several versions. Here, we pick the relatively easier version. What's that? Because the harder version should be in this way. The fake coin has different weight than the normal one, but you don't know lighter or heavier. You do not know lighter or heavier. Here, we know it's lighter, right? Oh, let me change the color of the pen. So this information is useful. Yeah. All right. This information is useful. We can use this information to help us reduce certain number of weights. But more challenging version, we do not know lighter or heavier. We just know different. The weights are different. Yeah. All right. So here, let's work on easier version first. All right. And greater than 2, and we did 3 last time, right? So pretty easy. Yeah, we just put 2 coins on 2 sides, 2 pans of the scale, but 1 off the pan. Yeah. So here you can see for all the coins we consider, there are 3 different status. 3 different status, not 2. I remember last time one student, probably Dakota, if I remember, said split into 2, right? Yeah, 2 piles, 2 groups. Yeah, but here you can see you have the option to split into 2 groups, but look at the status. We have 3 different status: left pan status, right pan status, off the pan status. If you want to use all the information, all different status, all the information, it's better to split into 3 groups, 3 piles, 3 groups. Because if you split into 3 groups, you can reduce the number of each group faster, right? If you split into 2 groups, slower, the size reduction will be slower, right? Divided by 2, n over 2, right? Yeah, so here, some students probably not follow that. Think about, if we split into 2 even groups, n over 2, each group n over 2, okay? Another way, if we split into 3 even groups, okay? Yeah, we can put the, floor function, right? Floor function, because it must be integer, right? Floor or ceiling function. And we know the second expression is smaller than the first expression. So the size reduction will be faster. If the size reduction faster, we need a fewer number of waves. So that property, here we are talking about special property. That property is useful. So keep in mind, yeah, so we will use that. All right, so let's continue. Let's continue our discussion. All right, oh, yeah, erase that. All right. Solve the simplest case, we did it, right? It's trivial, but here I want to run the diagram from beginning to end. We have 3 identical looking coins, 1, 2, 3. So now we just pick coin 1, coin 2, and put on the balance scale in this way. And we will have 3 different cases, okay? 3 different cases. 1 in the middle, balanced. In this case, which one is fake? 3, yeah, fake, okay? Another case, which one is fake? Lighter one, number 1, okay? 2, all right? So 1 way, we find the fake one, right? Yeah. Now we move to the general case. Although last time I gave you n equals 4, yeah, but here let's jump to the general case faster because I want to save some time. Okay. All right. For the general case, there are 3 states. I just talked about 3 different status, 3 different states. Right. Left pan state, right pan state, off the scale state. 3 different states we need to consider. Okay. But when we have freedom to distribute all the coins in these 3 different states, the question is, what is the best way to make the distribution? The best way. Yeah, think about that. Yeah. Because we have a lot of different ways. What is the best way?
So I was talking about the 2 different groups initially.
Uh-huh.
So I was thinking we were working with more than 1 point at a time. So if we had 2 even groups, we could figure out which one was lighter just by the sheer number.
Yes, you can. You can do it that way.
That's similar to 3 groups too, because if you have 2 groups and they're equal, then you know the 3rd group is a little bit lighter.
Right. Think about size reduction. That way will be faster.
That is true.
Yeah. You can do that, but slower. All right. Yeah, we want to find the best solution. Think about that. Best solution. All right. So here, when we have freedom to distribute all the coins into 3 different groups, the best way, here there is a general principle here, how to divide. The general principle we call the balancing principle. Try to balance the distribution or even distribution, as even as possible. Okay? As even as possible. That will be the most efficient way. Balancing principle. Data distribution. Here we distribute our data in a balanced way. Balanced way. Now, later you will, in this course, when we learn more and more, later you will see the most balanced data distribution would correspond to the best case solution. Best case solution. If you distribute in an extremely unbalanced way, that will correspond to worst case. You want to get the best case. You don't want to get the worst case, right? Yeah.
So best case would be if we had a number of points that are divisible by 3.
Sorry.
Like in this case, would our best case scenario be if we had n number of points that's equal to 3? If we divide it, it's no remainders. Right.
Yeah, no. Regarding the remainders, that's another factor. We need to consider remainders. Remainder is important. You cannot ignore that. So we delay it a little bit. Remainders. Now, next slide, we will work on remainders. Okay, all right, yeah. So here, this is the first time we apply this balancing principle. Later we will also apply, but the concept, when you try to distribute your data as balanced as possible, you will always get a better solution. If, unbalanced way, the difference is big between different groups, that will correspond to worst case. Much worse, yeah. We will see that. Yeah. So here, the first time we look at that question, next, all right. All right, this time from simplest to general. Now we consider the general case. But when we consider general case, there, remainder, because we may have different remainders. When we n divided by 3, how many different remainders?
3, we count 0 and 2.
Yeah, we have to count 0. 0, 1, 2, 3 different remainders. And which one you feel the easiest? 0. No remainder. So here, when we solve any problem, general problem, we always work on the easiest first. So we work on the remainder 0 first. Let's work n equals 3k. The student, you just came in. Okay. Yeah. Just remind me, but I need to check your name later.
Oh,
attendance check.
Okay.
Yeah. All right.
Appreciate it.
Yeah. So n equals 3k, remainder 0. The 3 groups, even 3 even groups. Yeah, like this. 1, 2, 3. 3 groups. Okay. I put subscript k. So each group has k coins. Okay. All right. Then we run our general procedure. Put on the scale. Yeah. 3 cases, right? Think about 3 cases. The first one, the fake one is in group 3, right? Yeah. Group 3, fake. Fake one in group 1, group 2. Now you can see the size reduction. What is the size reduction when we run this way? From original size n to size k. How about that? That's the size reduction. From n to k. Okay? Yeah. Can you work on k coins? So after one weighing, you only need to consider a group of coins with k coins, with 1/3 of the original number of coins. How about that? One way reduce the size to 1/3. Is that good? Is that efficient? All right, yeah. All right, conclusion, size reduction. This size reduction way, that's a general way. So later when we solve many other computing problems, we do size reduction all the time. Okay, the question, how to do the size reduction? Yeah. But this idea, we do all the time, size reduction. Okay, from n to k. Yeah. How to handle the case that n is not a multiple of 3, remainder 1 or 2. Because we solved the remainder 0 case. Next, we move to remainder 1 case. All right, this time n equals 3k plus 1. Then, look at the 3 groups in this way. We distribute the coins as even as possible. Now, although not perfect, even way, but the best we can. All right, k plus 1. Okay, all right. Then let's, so group 1, group 2, fake in group 3. All right, so fake. Yeah. All right. Then this time size reduction. Yeah. From here we consider the worst case. Yeah, because we have 2 better cases, right? Yeah, 2 better cases. But when we have different cases, we focus on the worst case. The reason is simple. If we can solve the worst case, then we can solve any case. If we have a solution for the worst case, then we can only do better for other cases, not worse, because we already take care of the worst case. So here we focus on the worst one. So the size reduction from n to k plus 1. A little worse, but still pretty good. Yeah, so we take it. All right. Yeah, it's the worst case. All right. So the last case, remainder 2, 3k plus 2. Right. So this time, 3 groups in this way. Okay. Yeah. All right. Let's run. Yeah. But this time you can see, yeah. All right. So here, the general case, the size reduction. So here we write a general size reduction. This is the general size reduction. From original size n to the seeding function, not floor function. Okay? Here we use seeding function, not floor function. Seeding function of n over 3. Why? Because this k plus 1, we take the seeding function. Okay? Here, for this case, we need to consider the worst case. We need to take k plus 1 also. So that means we should take the seeding function here. Okay? All right. Yeah. So then for the, all right. How to represent the minimum number of weighings in terms of n. Now, so our last step, we need to find the number of weighings as a formula in terms of n. In terms of n. N expression. Using n to write a formula. Our last step. Okay, all right. What is the simplest case? When we do this, at this point, if I ask you to write that formula directly, it could be hard, right? Think about it. Do you feel hard to write that formula immediately? Do you feel hard, right? Yeah, it's hard. Question? No.
I was thinking it had something to do with the logarithm.
Yes, log-based what?
Okay.
Log-based. How many groups we split? How many groups we split?
N?
3. Log-based 3. Yeah, that number of groups determine the log-base. Log-base. All right, but that jump is too fast. Okay. Yeah, that jump is too fast, right? Yeah, I will go there. I will logarithm. Yeah, many of you are scared about logarithm. Yeah, but for this class, we use logarithm a lot. You know, when you go home, study the algebra properties for logarithm a little bit. Yeah, so we will use the logarithm a lot.
Because it's a logarithm growth. So as we add more, it's not multiplication.
Yes.
It's simply a
exponential.
Yeah.
Exponential.
Yeah.
Exponential function reduction, much faster. All right. Yep. We will get there. All right. So here, let me tell you my goal. I need to derive that formula for the number of minimum weighings to find the fake coin for n coins. Yeah. But remember, when we have multiple cases, remainder 0, remainder 1, remainder 2, we have many different cases. We always pick the easiest case first. Remainder 0. Okay, remainder 0. So that means n is a multiple of 3. That's for the first split, right? How about second split? Another split. Another multiple of 3. How about third split? Another multiple of 3. How about fourth split? Another multiple of 3. All the way multiple of 3. How about that? That's the easiest, right? Yeah. Whenever we split a group of coins, we assume the number of coins in that group is a multiple of 3. Is that the easiest case? Yeah. That's the best we can think of. Best thing we can ask for. All right. That will correspond to n equals power of 3. Because n can, when you divide n by 3, it is always multiple of 3. So the only n that allows us to do that, power of 3. All right, so let's, yeah. All right, the simplest case, all right. We assume n is the power of 3. First, Yeah, because we want to work on the easiest case first. That's important. Yeah. Easiest case first. Power of 3, that's the easiest case. Okay, so let's work. Let's assume n equals 3 to the kth power. Kth power. All right, yeah. Now, if n equals 3 to the kth power, how many weighings do we need to find the fake coin in this group?
So is that's for the log base of 3 and 10%?
Yeah. Don't guess, don't get, all right. Here, let's run the, left column size, right column number of weighings. Okay, let's run it. Okay, try to find some rules between these two columns. All right. Yeah, so here, at the beginning, before we do the first weight, the size is 3 to the k. And here, we haven't done anything. The weighing number that we have done, 0. At the beginning, 0. Okay, the size is 3 to the k. All right. Now, let's do one way. We can do one way. After one way, what is the size? Divided by 3, right? Original n number divided by 3. 3 to the k minus 1. Because this number divided by 3. Think about that. Divided by 3. All right? Yep. Okay? All right. So the exponent number becomes k minus 1, reduced by 1. Second way, another division by 3, right? Let's do another division by 3. How about that? Okay? Can you see some rule? When we do experiments like this, can you see some rule? Straightforward rule. Observation. What's the rule? Special property you can find. Yeah, look at the numbers. You can see, find some beautiful rule, all right? Not ugly rule, some beautiful rule. Is there any?
The W value.
All right, look at these numbers. Left-hand side, look at the k, only look at the exponent number, all right? Right-hand side, this number, look at the exponent number. Right-hand side, that number. Any rule you can see? Ignore that 3. Ignore that base 3. Anything special you notice? 1 to 1. But we want to find some beautiful rule. Yes, we either, feel. It's so good. Yeah, we can feel about it. Beautiful math. A good math must be beautiful math. Think about that.
We're decreasing the x. Right.
All right. Give you a hint. Add 2 numbers each row. What do you get? Add 2 numbers each row. K plus 0, first row, k, right? K minus 1 plus 1, also k. K minus 2 plus 2, also k. Any rule, any special rule? The 2 numbers, the sum of the 2 numbers each row, the same number. Is that good rule? Is that a good rule? The sum of two numbers each row is a fixed number. It never changes. You run from top to bottom, row by row. It never changes. Is that a good rule? Is that a good rule? Never changes. But not beautiful. You feel not beautiful. All right. Here, a good concept. It never changes. We call it invariant. Invariant. No change. There is a property. Invariant is important. Yeah. So in math, in problem solving, invariant number is always the most important thing. If you can find some invariant number, very important. Here, let me introduce this important problem-solving method, invariant method. Okay, all right. Here, consider this quantity, E plus W, E exponent of left column expressions, exponent E. E plus W, right column number, always the fixed number K, so we call invariant. Okay? Why invariant is so important? Think about why invariant is so important. Because if we know this invariant number, we won't get lost. When we go from top to bottom, we need to do things like dot, 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 right? We need to do things like dot, dot, dot. Why you do things like that? If we do not know the invariant, we get lost, right? How do you know what's in that dot, dot, dot? We don't know. Okay, all right. But after we know that invariant, E plus W equals K, now I ask you, if dot, dot, dot in some row, this number is 16, what is the number? Corresponding exponent number? 16. The exponent, what is it? Do not look at the base 3. Only tell me the exponent number.
A minus 16.
Yeah. So easy, right? Yeah, because you know the invariant. So powerful, invariant concept. Invariant concept. Is that important? Otherwise, how hard you will find that number K minus 16 exponent number. Think about that. Next time, I remember I saw some interesting puzzle question before. In that one, invariant concept plays a brilliant role. Yeah, so beautiful. In that special example, invariant thing, the concept. It's hidden, it's very hard to find it, but it's so important. I remember there is a puzzle question. Yeah. So if I can find it, I remember I read it in a book. Okay. If I can find it, I will show you invariant concept. All right. Yeah. Yeah. So now when we reach the bottom, it's so easy. When we reach the bottom, but because the size reduction, the last row, when we find the fake coin, the final weighing, the fake coin must be the singleton, right? The single one, the right one. So this is the fake coin. One group, one final group, it contains the fake coin. Is that one? 3 to the 0. How many weighing? Based on the invariant relationship, K weight. How about that? Is that the answer we want to have? K. Yeah. But it's not in terms of n, right? The requirement, we need to represent this K in terms of n. Logarithm. How to write K in terms of n? Log base 3 of n log base 3 of n. That's the final formula. That's the final formula. Hard to follow, or you feel okay. Yeah, we have a little more time. Study the video another time. That's the good thing. I record the video. All right. Yeah. So you have a weekend. Yeah. Hopefully you can use this weekend to digest this puzzle question.
So like the main point of the invariant is to just keep track of where we are in like
yes
the process.
Right. Keep track of,
because overall the e plus w, the exponent plus the I guess iteration on is equal to our k value.
Right. Yeah. Later we have a few more questions. We need to use this invariant concept. Okay, we have a few more. Yeah, this concept is so important. Yeah, I will try to find the puzzle question I just mentioned. Yeah, that question is so smart. Yeah, I have to find it to show you the power of invariant concept. Okay, yeah. So it's a chessboard question. All right, special, another chessboard question. So brilliant. Yes. All right. So, yeah. Next week, I will show you that. All right. Now, because we only consider a special case, n is the power of 3, that's not a general case. We need to consider the general n. So we need to make another step forward to the general k. Okay? All right. General k, yeah, because in the general k, this log base 3 of n is not an integer, right? It's not an integer. Only when n is power of 3, it's an integer. So for the general case, it's not an integer, but our weighing number must be an integer. So we need to convert this formula to an integer expression. Here, there are two different ways we can take. Floor function way and the seating function way. Floor function way, seating function way. These two easy conversion ways. But which one you feel should we take? Which one? Floor function way or seating function way?
Well, we're trying for the worst case, right?
Yeah, worst case.
Worst case. Then wouldn't we use the ceiling function?
Yes. Worst case, round it up, right? Round it up. Seating function. Okay? Yeah. All right. So here, our final solution. Yeah, let's look at the final solution in this way. Okay. Given a general n, here, arbitrary n greater than 2, yeah, we want to find some k, integer k, such that n is between these two numbers. N is greater than 3 to the k power, but strictly less than 3 to the k plus 1. The question, can we do this all the time? Think about it. Is it possible we do this all the time, this inequality? We can always find such k. And n must be between these two power of k. How about that? Can you imagine that? Should be correct, right? Think about it. Should be correct. Any doubt? Some students still not feel comfortable. All right.
Why isn't it k plus 2 versus k plus 1?
K plus 1. So here, k plus 1. K plus 2.
Yeah, why is it not k?
Yeah. Good question. K plus 2, the gap is bigger. We want to make the gaps as small as possible. The gap between two adjacent numbers, two adjacent power of k. the gap smaller, yeah, always narrower, the smaller the gap, the better. Question?
Isn't it because though, we're not actually, this isn't about the remainders. This is just about, like, for each group of three we have.
Here, we do not consider remainder. Remainder too complicated, right? Too complicated. So here, we do not consider remainder.
Yeah, that's
So,
what I figured.
yeah, let me draw a diagram to show, just show why this inequality always true. Yeah, all right. So I only draw power of 3 on this number axis. I only draw power of 3 number axis. Okay, all right. 1 equals 3 to the 0, right? So the first one, okay, all right. 3 to the first, right? All right, power of 3. May not be scaled because I do not have a lot of space, okay? May not be scaled. 3 squared, that point, I only draw power of 3, okay? All right. And so on, all right? Okay, yeah. Then we look at that n greater or equal to 3, right? So n should be at that side, right hand side of the 3, right? The n should be here. Okay, yeah. Anywhere n, so you just take it. It must be between 2 adjacent power of 3, right? Right. So from this diagram, so anywhere, because we allow equal sign. Okay? If I take away that, it may not, because you just take the power of 3 theoretically. Here I allow that equal sign of inequality. So you can always find 2 adjacent power of 3 for, and the interval, the corresponding interval contains that n. How about that? Okay, all right. So after we have that, then look at the number of way. Number of way. Yeah, because after we have that formula, when we solve this problem for 3 to the k weighings, okay? Yeah. When we solve that 3 to the k plus 1 weighings, and the n has more coins than that 3 to the k's, but less than 3 to the k plus 1, think about the number of weighings we need. The best is k, the worst is k plus 1. But that number must be an integer. Cannot be a fractional number. Yeah. So the answer must be log base 3 of m seeding function. Go moving up. Okay, not moving down, moving up. Okay, yeah, that's the final formula. Okay. Question. Now I'll give you time to ask question.
So basically that inequality just is proving the fact that a log base 3 of n is in fact the worst case scenario that it'll take on. That's what the inequality represents, that
right.
Has that best case or worst case scenario.
Best case, worst case. All right, so here, all right, here we consider sometimes quite confusing, best case, worst case. All right, yeah. So here we come, all right. We solve this fake coin problem always for worst case, right? Always for worst case. Okay, yeah. No matter what. Yeah, so here, I want to say, no matter what n is given, if it is between those two numbers, we can use k plus 1 way to do it, to find the solution. K plus 1, yeah. So, but that k plus 1 corresponds to the seeding function, not the floor function. Seeding function, moving up. So that's what I like.
Reason why it's not used to.
Yeah, not inclusive here, right? Right. Because if the inclusive here, we move to the next one. Yeah, same pattern, yeah, that's a good question. Yeah, why not inclusive? Because, all right, first we want to make the slot as small as possible. If we include it, you make your slot a little larger. So we can do better removing that equal sign. But second, because if equal case, can we consider the next slot next to an adjacent power of 3? We can consider next to an adjacent power of 3. Okay, yeah, yeah. All right, so here you can see we need to do a lot of logic reasoning. Okay, yeah, try to get used to it. All right, still you feel turn on the light or off at this point, you know, to, yeah, let's try this way, which one you like?
Something else.
I'm still, no.
All right, off, another round, okay? Another round until you tell me on. Yeah. All right, so we finished part A. This is part A. Okay, yeah. Yeah, I plan to use 30 minutes, but it looks like I used much more time. Yeah. All right, yeah, but think about how many concepts we talk about here. A lot. All right. Yeah. Yeah. So let's move to part B. The remaining time of today's class, let me do the part B. Yes. This is another question.
Share that.
Yes. Yeah. Yeah. I will. Yes. Yeah. Actually, right. Yeah. So you do not have to take the notes. I share with you my PowerPoint note, 2 versions. First version, the original PowerPoint file. Second, my annotated PDF file. Annotated PDF file. So you can get everything, and also the video can help you, you know, go through all the details. Yeah. All right. So now we move to part B. Part B. The title, Efficient Polynomial Evaluation. This is another simple but interesting question, and we will do our first programming project based on this topic. First programming project. Okay, all right, so let me, yeah, I need to change the pen color every time when I start a new PowerPoint slide. I need to change my pen color. Okay, all right. Yeah. For this topic, I need to use 3 subtopics, B.1, B.2, B.3, to complete, you know, the whole story. The first one, evaluate the polynomials. So when we start, that's all of you know how to evaluate a polynomial, but we want to see what is the best way? What is the fastest way? What is the most efficient way? And also we want to compare the difference, most efficient way and the, ordinary way. So here I want to say ordinary way, because most people use that ordinary way. Okay, all right, let's start. Our problem number 2 for this class, evaluate a polynomial. Given a polynomial, you know the polynomial, the definition. Okay, that's the general expression for this polynomial. We have coefficients n0 and 1. That's we call the coefficients. The variable x, single variable x. So the coefficients, when they are given, then we fix it for one polynomial. We fix all the coefficients for one polynomial. But we can change the value of x. Every time when we change the value of x, we want to calculate the polynomial function value at x point. Yeah. The question: how to evaluate p of x efficiently? The fastest possible way. That's our goal. Yeah. Because we may have many different ways to evaluate a polynomial. You may probably only know one, but actually there are more than one. Okay? But which one is the fastest? Okay, all right, yeah. Let's do analysis. All right. Here, the ordinary way I mentioned, everybody knows. When you have a calculator, you know how to find the value of a polynomial. Okay? Basically, you do multiplications and additions. Okay, yeah. Just the way you use to find the value of polynomial using a calculator, or you write a program, computer program, you can find its value. Okay, yeah. If we use that way, so here I just temporarily refer as ordinary way. Why we need an algorithm, right? Although that we can treat that as an algorithm, why we need other special algorithm? That's the question. Okay. All right. Yeah. Here we whatever way we do, we always need to use addition and multiplication operations, right? Yeah. You can do in so many different ways, but you need to do additions and multiplications to find its value. Okay, yeah. Here, how to measure efficiency. Yeah, because here, think about, suppose we have several different methods. We can calculate the value of the same polynomial. Suppose we have more than one, several. The question is, how do you measure efficiency? How do you tell me one is more efficient than the other? That's the question. Okay? Yeah. We want to know that. Yeah. Go ahead.
You would usually measure efficiency in the amount of time it takes, right?
Yes, that's the most straightforward measure. Amount of time, clock it. Okay? Or, in our computer program, we can clock it. There is certain functions we can use to find the time. So that's the most straightforward measure. We can call response time. response time. We use the response time. That's the first measure, direct, straightforward measure, right? Yeah. For the question, yeah, you can use that to compare one algorithm is faster than the other. If I ask you a deeper question, suppose we run those two different algorithms on different computers, not the same computer. Can you still use that way to do comparison? What? Yeah, computer hardware different. One is supercomputer. One is multi-core super 128 multi-core computer. Another is low end. Yeah, very. Yeah.
Or if your computer is pretty good with like whatever your input values are just extremely large in the program. Normally it's very fast, small, and it's might be very like cumbersome with the values of the bigger.
Yeah. So
are you asking the size of the time? What else is there?
yes.
For measuring?
Right.
Measure space?
Right. Yeah. Oh, yes. State amount of state. Yeah. That's we do not call measure. We call it another factor to be considered. Amount of space. Yeah. Well, not measure. Not measure. All right. Yeah. Position. Yeah. Precision. Still not measure. Yeah. Still not measure. Oh, so many students. Number. Yeah. Good. Yeah. Very close. You also say something.
Yeah, like comparison.
Oh, yes. You too, the closest answer. Yeah. So another way. All right. So here, this response time, we feel not stable because the hardware factor is important, right? Yeah. Here we don't want to consider the hardware, right? We want to take away the hardware factor, right? So there, another measure that is more stable, more fair, more stable, number of operations, or number of additions, number of multiplications. Yeah. If we use number of multiplications, number of additions, then we don't worry about which computer we use, right? Yeah. Yeah, think about that. So this is another important concept. Yeah, so we will talk about that more. This is the first time we see this question. All right. All right. Execution time not stable. Right? Here, answer not stable. We want to find a stable, better measure. All right. So here we use the number of additions and number of multiplications, more stable. Number of operations, more stable. Okay, all right. Now let's try it. Let's work on it. Yeah. So for the given polynomial, let's count number of additions, number of multiplications. How about that? Can we do it? Yeah. Counting. Here we need to do counting. In discrete math, you learn the counting techniques, right? Math 3000. Yeah. I try to remind you counting techniques, basic counting techniques, not advanced. All right. Now let's do the counting. The first time we do the counting, the straightforward math algorithm, just multiplication, addition, when you find the value of this polynomial, the normal way. Okay. Yeah. The question. So here, let's consider number of multiplications first. Number of multiplications first. We have many terms. Tell me, how many terms do we have in this polynomial? N plus 1. How do you know it's n plus 1, not n? Anybody can explain to me n plus 1, not n?
Because we're including, and like we're including x to the 0.
Yes.
Which is 1, so that make that a to the 0, a sub 0.
Yes.
Right?
Because when we do the counting, we start from 0, not 1, from 0, 0, 1, 2, 3 through n. That's n plus 1 numbers, not n numbers. Okay, yeah. So we have n plus 1 terms. Here, we want to consider a general term. What is the general term? Here, we write the expression of general term. A sub k times x to the kth power. That's the general term, right? Yeah. When k equals 0, that's the first term. When k equals 1, the second term, and so on. So we can use this general term to represent arbitrary term by changing the k number. Okay, yeah. Here, for this general term, we use it as a representative. This expression can represent any term in the polynomial. Yeah. Let's do the counting. In this general term, in order to find the value of this general term, how many multiplications do you need? Multiplications. No addition, so we only have multiplication.
Would it be k plus 1 because you have however many times you're multiplying x by k times, plus you have to multiply it to a, so that would be k plus 1.
Yeah, all right. Yeah. Some of you went through part A, right? Tuesday's class. Definitely not all of you, some of you, right? Yeah. In that class, we learned a strategy. Yeah. When we do data processing, here we do data processing. Okay, we count the number of multiplications. We do certain data processing. If the data is relatively complicated, here, yeah, because this k can vary, bigger, smaller, relatively more complicated. What strategy in this situation? What strategy we use when we have this kind of situation? We do experiment for the data size relatively small, right? Yeah. We work on the simplest cases. Think about that. That's the strategy we learned in part A. Okay. When we need to do data processing, when we start, we work on the simplest cases first. That's the strategy. Okay. Here, tell me, when k equals 1, how many multiplications do you need to do? K equals 1, only 1. How many? When k equals 1, you have a1 times x. How many multiplications do you need? Calculate. How many multiplications do you need? 1. When k equals 2, you have x squared. How many multiplications do you need? X squared, do you need a multiplication for x squared?
Yes, just one, right?
Oh, it's, yeah, it's x times x, it's multiplication times a is.
2, right? Right? Yeah. When k equals 3, how many multiplications do you need? 6. Just think about one more than this one, right? One more.
So it's that same invariant. The same type.
This time not invariant, it changes. So it's, yeah, it changes. Yeah.
Oh.
But there is a rule. Okay. Can you observe the rule? We do 3 experiments. K equals 1 experiment. K equals 2 experiment. K equals 3 experiment. Can you summarize some special rule after these experiments? Yes, K multiplications. K multiplications. How effective is our strategy? Our strategy, we start with the simplest cases. That's our strategy. All right. That strategy looks nothing, right? That strategy is so trivial, but effective. Because if I do not mention that, nobody may apply that strategy, right? Think about it's effective. Okay? Yeah. Good. All right. So the answer is K multiplications. Okay? Yeah. All right. The reference of this topic, yeah. Here, I give you the reference in the textbook, section 6.5. It's some later section, but it's not too hard. Polynomial, you know polynomial well. And we want to do our project number 1 on this topic. So that's why I start this topic earlier. Okay, all right. Is your algorithm efficient? So here, the next question. Here, each term, K multiplications, so we can calculate the total number of multiplications. So here the question. Is your algorithm efficient? We don't know, right? Because we only have one algorithm. If you cannot compare it with any other different algorithm, how do you know it's efficient or not? You do not know it's efficient or not. Only one. Only one. So that's the only one we have. Okay? But if you have more than one, then you can answer this question. Okay? Because the second one, you want to see if it's better than the first one or not. Okay? But here we don't have the second one. Okay? If we can find the second one, then we can do comparison. Okay? All right. Yeah. Question. Are we satisfied with the solution? At this point, we may not know it, right? So if I ask you, are you satisfied? Probably you will say yes. Because if that's the only way you can do, if that is the only way you can do.
I'm guessing there's another way to do it?
Yeah, another very smart way, super smart way, super smart way. Otherwise, yeah, why I spend time here, right? Yeah, there is a super smart way. Okay, all right, let's take a 15-minute break.